Okay, we're on explore number 3. Go ahead and write out your template notes there. Go and write the date. And you can go ahead and take that essential question in green. What are some examples of conversions between kinetic energy and potential energy in the world around you? All right, so write what you know. Okay, write what you think. Okay, hopefully you took a moment, you hit pause, and you wrote something down there before we begin the notes, right? Now let's actually take this reading and make sense of it. Roman numeral 1, conversions between kinetic and potential energy. Conversions. Changing, right? Between kinetic and potential energy. Conversions. Between kinetic and potential energy. Okay, there are two important facts to remember about energy. The first, the total energy in a closed system, there's the key. The closed system is always conserved. Okay, that's an important point. Two important facts. Number 1, in closed systems, total energy, that's all the different types of energy, potential energy, kinetic energy, total energy is conserved. It is constant. Okay. You have an increase in one, you're going to have a decrease in another, but when you add it all up together, it's always going to equal the same. Number 2, while the total energy in a closed system is constant, the energy within that system can change from one form to another. Okay. Within this closed system, energy can change from one form to another. Okay. Okay, so we're just kind of making sure we got all of our notes there. It's all visible. A common example for energy conversion takes place when objects are in free fall. Read these next couple paragraphs, okay? I'm not going to read them all for you, but you know the drill. Make sure you read it, okay? But what I do want to do is I want to jump down and get into some examples here, okay? So they give this example of an apple on an apple tree. It has a mass and it's resting at a particular branch. They're going to say that it's at branch that has a certain height, h1 above the ground. At this time, because the object is at rest, the total energy of the object is in the form of gravitational potential energy, which is given by the equation potential energy is equal to mass times gravity times height 1. Okay, so we're going to go ahead and we're going to just map this out, okay? We'll say this is letter B. Example. Okay. You have an apple You have an apple tree, right? And we have an apple on the branch. Right, we have an apple. And it's at a certain height. Height 1. Okay. So we could go ahead and say that the potential energy for this system, potential energy at this height is the mass times the gravity times the height at height 1. Now assume that at a later time a strong gust of wind loosens the apple, causing it to fall. It loses potential energy and gains kinetic energy, such that it falls to a new height, h2. And so it's going to have a new potential energy. So we could go ahead and say that the wind blows and our apple is going to fall. The apple falls to a new level because of the wind. And so here's our apple. It's now at a new level, stuck on another branch. And we're going to say that this new height is h2. So now our new formula, because it has a different potential energy now, potential energy 2 is equal to the mass times the gravity. Those don't change, but the height has changed. Okay. So, and we're just kind of working through this right now. So the loss of gravitational potential energy is given by this equation. Delta PE, that is the change in potential energy. The change in potential energy would be your potential energy number 1 minus your potential energy 2. That's the height difference, right? Which, as you know, would be the mass times the gravity times the height at level 1 minus the mass times the gravity at height number 2. Now, they kind of go through and do a little bit of fancy math here, which should not scare you, but we can go ahead and do the distribution principle here, and we can pull out the, sorry there, not sure what happened. Oh, geez, what did we just do there? Don't want to do any of that. Hopefully everything is still recording here. We can go ahead and say that this equals mass times gravity times h1 minus h2. So notice what we did was we took the two terms that were common in both expressions, right? The mass and the gravity were common in both expressions. So we were able to pull them out and put them in front of the parentheses. This is a distribution principle here, and then just put the h1 minus h2 in parentheses. Okay, now this equals the change in potential energy. Okay. The other thing you have to understand is in a closed system, if you remember there, number 1 up here, in a closed system, total energy is conserved. Energy can change from one form to another, it can change from kinetic energy to potential energy, but it will be conserved. And so down here, then you can see that the change in kinetic energy in the system has got to equal the change in the potential energy. Okay, so let's just go ahead and write that down, okay? The change in kinetic energy in the system has got to be equal to the change in the potential energy of the system. Okay, this sentence here, the loss in potential energy, delta PE, is equal to the gain in kinetic energy, change in kinetic energy. Thus, the change in kinetic energy of the apple is given by delta KE equals delta PE. So there you can see that in essence, we can say that the change in kinetic energy is equal to the mass times the gravity times h1 minus h2. Now, when you think about change in kinetic energy, you have to think that kinetic energy, let's just write this out as a side note, Ke equals 1/2 times mass times velocity, right? Well, at the beginning, at the first height, there was no kinetic energy. There was only potential energy. Okay, so we're going to say, so really what we had was we only had kinetic energy at the second height when the apple dropped. Okay, so at this, so we can say, we're going to say there's, theoretically, you have a kinetic energy 1, which is the half times the mass times the velocity 1. And you should have, this is what delta, and you should have a kinetic energy 2, which is a half times the mass times the velocity 2. And you should have that delta KE is equals KE1 minus KE2. But remember, there's no kinetic energy 1 because the apple was not moving. Okay, so no kinetic energy at position 1. At position 1. Okay, so what is our change in kinetic energy? Our change in kinetic energy is just going to be a KE2, 1/2 times the mass times the velocity 2. And this velocity 2 would basically be the final velocity when it fell, velocity, right? So really we can say is that this is equal K, this is the change in kinetic energy is going to be equal to the, it's going to be 1/2 times the mass times the velocity at height number 2 is equal to the mass times the gravity times the height 1 minus the h2. Okay. All right, so I kind of walked through there. I tried to hopefully explain the thinking behind there. And what we did was we really were exploring this idea right here. How the change in kinetic energy is equal to the change in potential energy. And this is what's interesting. The last equation, this is important here, is very helpful in solving problems of motion. In fact, it applies not only to objects in free fall, but also to objects that are traveling up and down inclines, such as roller coasters and skiers. Okay, so this formula is a very, very important formula. You're going to be using this, okay, to help you solve some problems. Okay, well, perhaps we should go and actually take a look at a problem, okay? So we'll go ahead and take some time and explore the example problem, okay? Example problem. You have a roller coaster car loaded with passengers that has a mass of 1,300 kilograms. The first drop of the roller coaster is 64 meters above the ground. The bottom of the first drop is 15 meters above the ground. assuming that the roller coaster comes to rest as it reaches the top of the first drop, determine its speed at the bottom of the first drop. Okay, so we have a roller coaster. We got this roller coaster, and it drops down. Now, let's just say that this is the ground. Okay, this is the ground. And we're going to say that you got to have poles or something to hold your roller coaster up, right? Do that. And we'll say that maybe you have something holding it up way up here. Okay. So your roller coaster, there's your, you got all these people in it, right? And the mass of the roller coaster is equal to 1,300 kilograms. The height of the first drop, right? The first drop is 64 meters. That's how high it is from the top to the ground. At the bottom of the first drop, we have a height of 15 meters. Okay. And they want to know, assuming that up here it was at rest, velocity 1 equals 0 up here, or velocity initial equals 0 up here, they want to know how fast, what was the velocity final right at the bottom of the first drop. Okay, so what do we want to do? We need to figure out, determine its speed. That's velocity, right? Which of our formulas is going to solve for velocity? Well, we have two equations. We have a kinetic energy equation, which is 1/2 times mass times velocity squared. So there's a velocity. And then you have another formula. You have the potential energy formula, which is the mass times the gravity times the height. So the potential energy formula doesn't really help us solve velocity. But you've just learned that you can, in a closed system, you can make the change in kinetic energy equal to the change in potential energy, right? So what can we do here? We've got mass. We've got the gravity, the acceleration due to gravity, 9.8 meters per second squared, and we have the h. So we could say that there's a potential energy. Okay, so let's just put this here. Okay, we're going to say that you have potential energy initial, or potential energy 1, is going to be the mass times the gravity times h1. The potential energy final is going to be the mass times the gravity times the height 2. And going off of that formula, we could say that the change in potential energy is the mass times the gravity times the height 1 minus the mass times the gravity times the height 2. Using the distribution principle, we could say mass times gravity is pulled out of that, and we say is h1 minus h2. Close that parentheses. And this is the change in potential energy. Now, we could say that what's the kinetic energy here? They did tell us to assume that at the very top there was no velocity. So kinetic energy initial equals 0, right? Because there is no velocity. So what is the kinetic energy? So therefore, we could say the change in kinetic energy is simply equal to the kinetic energy final. And we could say that that is going to equal 1/2 times the mass times the velocity final. And we're going to square that, right? Okay, since you know that, and this is your delta KE. Okay, remember that delta KE is equal to, or change in kinetic energy is equal to a change in potential energy. So we could say that you have 1/2 times the mass times the velocity at the bottom squared is equal to the mass times the gravity times h1 minus h2. All right. Now we want to get v all by itself. So I'm going to just do a little bit of simplifying. 2 divided by 2 cancels out. If I multiply it on the left, I got to multiply on the right. I want to get the m all by itself. So now I'm going to go ahead and divide out the m. M divided by m cancels out. What you do to one side, you do to the other. In this case, the m divided by the m cancels out. And now the last thing I need to do is I have a v squared, and we need to undo that. So we need to take the square root of a v squared. That's going to give us v is equal to the square root of 2 times gravity times h1 minus h2. And that's it. Okay. So what we need to do now is we just need to put in some numbers. The square root of 2. Remember that gravity is equal to 9.8 meters per second squared. This is gravity due to acceleration due to gravity. Okay, that's a constant, so that times 9.8, right? And then what was h1 minus h2? h1 was 64, h2 was 15. So if we said, let's just put this off to the side here, 64 meters minus 15 meters, 5, 14, 13, 12, 11, 10 equals 9. This is 49 meters. So what we have now is we have the square root of 2 times 9.8 times 49. And if you go ahead and put that into your Desmos or your other calculator, you're going to come up with an answer that says that the velocity final is equal to 31 meters per second. That's how fast your roller coaster is traveling. Okay, 31 meters per second. That's our final answer. Okay, and this is how you arrived at that answer. Okay. That's really about it, honestly. Clear the screen here. You're going to take time to read that, okay? Watch these videos. You have a number of homework questions that are going to be asking you to manipulate these formulas. And we'll talk to you soon. Oh, you know what I want you to do? Write yourself a summary paragraph. Okay, so let's go ahead and do this here. Sorry, those little baby chickens are making a lot of noise, but that's okay. Summary, paragraph. All right, we'll talk to you soon, okay? Bye-bye.